Hi everyone, thanks for the wait. Good morning, first of all, and we are actually very glad to have you here. So today we are here for this Apple Labs Meetup 8 on Generative AI and LLM. Here now I call upon Deepak for our short company intro and we'll proceed forward for the presentation.
Hi guys, my name is Deepak and actually I joined Apple Labs in 2019. My previous company was an e-commerce product related company. So when I joined here, I saw a very significant difference, and I just want to start this with that. When I came here, I saw that variation and the types of projects we have and the technology stacks. Then the older company was, there was very significant difference. What do I mean basically is that time we were also very focused on game. We still have our 3-4 in-house development game on Play Store. You can also try out after this session. We actually, our stack is like really full stack. Not the developer, our company is really full stack. We start from the hardware design. We also get that hardware stuff done. We that done. Also, we do the software. So, I want to give you one example. The use case was that whenever you cross through some gate, this gate, right? You can just twist your phone, just tap it, and it will check your credential and it will just close and open the gate. Okay. So the thing is, we designed the whole hardware, how SDK will work, how network will work. We also developed the app. So the full stack I just meant. Okay. Domain wise, we have healthcare and the video, and means our core is that. Third, what we have is e-commerce related. So that is the business domain what we have. In terms of tech domain, we have you can say AI, and AI is used all the places. Means right now all the processing, all the software, it is kind of integrated. It's not something separate. Then web we have, cloud we have, embedded we have, hardware we have. In terms of tech stack, we use a lot of programming language. We start from C. We have like developed SDK and the core modules for the cameras and all those are done in C, C++. From there, we use Python for our AI prototype and all. Then we implement them in C++ again. Then we have JavaScript, React.js, all those mean stack. And then we also have Android, it's mobile development, Swift for iOS and Java for Android. Even Kotlin we are using. Recently, we started using Flutter for the projects where app is not very hardware based. If you are not doing something related to hardware, then you can just use any library instead of writing in Java and Swift. So we have this whole stack. In terms of our growth and all, I just want to say that in times of COVID, when many of the companies were firing, we were still hiring. And our growth is very stable, very stable. It is always positive since I joined. And also Akhil's vision, he is the CEO of this company. He has been, he still writes the code for the camera solutions and all. So his vision is actually that growth should be consistent instead of we just add people. So quantity is the secondary thing, but quality is the primary. So our growth is like that. It's very stable, it's consistent, it is in that term. And yeah, that's it. I just want to end with this. Thank you.
Thanks, Deepak, for that introduction. Now we'll proceed forward for a very small ice break session. Here I'd like to take pardon from the audience who have joined us online through YouTube stream. We'll just take 5 minutes to engage with offline people and then we'll proceed forward with the presentation. So, as you have all now known, when you have entered in the registration desk, you must have received one sheet which must be having one number. I'll just call out the number. You can come here and you can read out the question and answer the question. So, number 9.
question is like, what looks easy peasy, lemon squeezy, but is actually difficult lemon difficult. It was a bit tricky.
Something which is very difficult. There's something which you like it's very
Getting a job for fresher. It's very difficult.
Okay. So your name?
Rahul.
Okay. You're a fresher currently.
No, working.
Okay. Okay. Thank you.
Thanks.
Number 11.
Question is, which movie made you laugh hard? I can say good news.
Okay. Nice one. Okay. Your name?
Name.
Okay.
Thank you.
Number 13.
Hello, my name is Rajans. The question is, tell us about the place you belong to without specifying the name. So I would say the famous is Vada Pav.
Mumbai.
Mumbai.
Number 12.
Good morning, everyone. My name is Priyank. The question is, what is an easy item on your bucket list that you haven't done yet? So I would say a trek to Himachal Pradesh, Shikhar Mahadev. That's a trek I want to.
Nice.
Yes. And the last one which we have.
So, hello everyone, my name is Ravi. So, my question is, show your cell phone wallpaper, is there any story behind it? So, my wallpaper is default Apple wallpaper, it's a dark mode. So, I put it over here because it is relaxing to eyes whenever I use my cell phone. That's all. Thank you.
Thank you. Okay guys, so with this I'll just give a very small intro. I'm Mansi, I work here as an ML engineer, and now we'll proceed forward with the presentation. Today we have Kashyap with us. He had some emergency, he had to travel overseas, but he has joined us online. So yeah, over to you Kashyap.
A bit about the transform model. We'll go into some detail on about self-attention, and then we'll have some slides on prompt engineering and a demo in one of our applications and products that we have built. So, what exactly is generative AI? So before ChatGPT came in, if anybody said AI ML, I'm sure this image to the left is what would be coming to your mind. So, classification models was, everything uh, was basically ML was all about classification models. So, what is a classification model? You want to learn the probability of y given x. So, you want to classify is this either red ball or a blue ball, and what the model is learning is this discriminative boundary line. So it wants to learn the best line so that you can classify these two classes. Whereas what is generative model? So generative models are trying to learn the probability distribution of the input itself, of x, the input distribution. So you want to learn this red uh, or blue ellipse, and what you want to learn is that these, apart from these samples that you are already looking at, you also want to know where the unknown samples would be so that you can try and generate them. So how generative AI has become as big as it is now is because of transfer learning. So before, people used to just have small data sets. They used to train very domain specific models. And, if you had a new task, then you'll go collect some more data, label that data, train another model. And this was very expensive and also very cumbersome. And now what people do is there are huge data sets. So there's ImageNet, for example. It's a huge image data set, right? That's where image classification really became big. So you have huge data sets and you train these very big models on these huge data sets. And then you try to just fine tune these models to specialize them for a particular task. So this is the current state, that AI is going towards. So we have the concept of this, foundational models and fine tuning. So if you see on the left, again, this is all text related, and on the right, it's all image related. So you have foundational models which are either, trained using unsupervised learning or semi-supervised learning. So you have GPT, you have Falcon 40B, which was, recently developed, and it's ranking number one. So this is an open source model developed in collaboration with Hugging Face in UAE. And then you have Palm. Palm is Google's LLM, and each of these LLMs are trained on large amounts of data, large corpuses of data. And then what you do is you basically collect some small amount of supervised, of labeled data, and then you train either specialized or domain specific models. So Chat GPT is a specialized model just for chat, whereas MedPalm is a domain specific model for medicine. Similarly, on the right side, you have these image foundational models, latent diffusion models, then diffusion probabilistic models. So these models are trained on large number of images, and then you have these specialized image generators like DALI, Midjourney. I'm sure you've all tried just putting in some text and creating an image. So how do we train these foundational models? So in the case of text prediction, if you see, the training paradigm is very simple. You basically have a context window, and what you're trying to do is you're just trying to predict the next word. So in this case, your context window is of size 4. So you have 4 words that go into the input, and then you're trying to just predict the next word. So just imagine, Wikipedia basically. So all of Wikipedia is dumped, and you call it DBpedia. So just imagine taking DBpedia, breaking it into sentences, and just trying to predict the next word. So that's a lot of data that you're just basically pushing through this very big network. And what it's learning along the way is this distribution of words, and it's learning that the is followed by a noun, for example article, noun, then there's a verb. So it's learning all these grammatical things without you specifically asking it to learn. It's just just trying to predict the next word, that's all. Similarly, in the case of image, what we're trying to do is we're going from data. So we're going from one image, we add a bit of noise, then we try to get back to original image. So, you keep doing that process until the model kind of learns to go from noise to a image. So if you see on top, this is a different dog image, but the one below is a very similar looking dog, right? But it's generated from this noise. So in both cases, you don't really need any labeling, right? Because you're just using the input itself and you're just predicting the next word, which is already there for you. And in this case, you're just adding some noise and then so this will be your target vector, right? This is your target, and this is your input. So you add noise, then you try to regenerate. Again, add noise, try to regenerate, add noise, try to regenerate. So we have, these foundational models, and how these foundational models get used in image generation. Uh, we will get into that now. So if you see this, this is like an encoder decoder architecture. So not all image generation models have this architecture, but the ones that we'll be talking about today, one of them does have this architecture. So I just wanted to describe, what the process is. So if you see on the left, this image of my cat, and we're basically going from this, W cross H cross color. So width, height, color, we're going into from this dimension, and we are encoding all the data. Okay, and we're trying to come up with a single vector, like a one-dimensional vector that has all this information encoded. So along the way, what we do is we perform, convolution operations, and we also do downsampling. So you take this image, you do convolution, you downsample, do convolution, downsample. Then finally you get this encoding, and then you do the reverse process. So you upsample, you do convolution transpose, upsample, convolution transpose, and finally you get this image again, right? So you're going from width, height, color to single dimension, and then back the other way. So before we get into more details, let's just brush up on this basics. So what is convolution? If you see, this is your input image. Okay, this is your convolution kernel, and this is the output. So convolution is the operation where you take the kernel, you basically just place it on the image. You do multiplication. So 1 into 3, 2 into 5, 1 into 2. So you multiply each position, and then you do a summation of those values. Okay, that will give you 55. Then you just slide this kernel to the right, and you do it over this part of the image. So in convolution, you have stride, which is how much you want to slide by, whether you want to slide by one column or more columns. Then you have the kernel size, and in machine learning, basically what you're learning is this filter itself. You're trying to figure out what these values are, and you do that by back propagation. So you have a final output, the target output, and then you have your predicted output. You see what the difference is, and then you try to train this, right? What we mean by training is basically finding out these values such that you get the desired output. Okay, so that's convolution. So that's what's happening on the left side of this image here. So we're going from big to compressed and small, whereas the converse of it is convolution transpose. So over here, what you're doing is you have this as your input. Okay, again, you're applying the same kernel, and you basically take this number 55, right? The first position, you multiply it by all the positions in this matrix. Okay, so 55 into 1, 55 into 2, that gives you one matrix. Then next, you go to the next stride. So, I mean, you go to the next value, do the same thing. So you get four matrices, and then you combine them all together to give you your final output matrix. So if you see, this output matrix and this input matrix, they are not the same. The numbers are different. So again, even in the case of convolution transpose, you are basically trying to learn these weights such that given this input, you want to come to this output, right? So this is where you have convolution, this is where you have convolution transpose. And at the end of the day, what we're trying to learn is these kernels. So in the case of image generation, there are these three qualities, three metrics that you want your image generation model to have. So you wanted to create high quality samples, of course, because if it's not generating high quality samples, then that model is pretty much useless. You want fast sampling, and the reason why you want fast sampling is you want to use it for applications. So for example, if there's a designer, right, and they have some ideas and they want to just quickly iterate over a bunch of ideas, and then select something to start working on. So the thing about generation is it gives you a good starting point instead of you having to start from scratch, right? So in that application, you want fast sampling because nobody can sit and wait for like 10 minutes or 30 minutes for a sample to be generated. And you also want mode coverage diversity. So what is this? This means that whatever you generate, right? You don't want your model to generate similar samples. So if a model always generates like 3 or 4 similar samples, then it's pretty much useless to you. So there are these 3 or 4 classes of models that basically have some qualities out of this. So for example, generative adversarial networks, also known as GANs. So they are good with fast sampling, high quality samples, uh, but they're not good with mode coverage diversity. Whereas denoising diffusion models, they're good with high quality samples and mode coverage diversity, but they're not good at fast sampling. And denoising diffusion models are basically trained over like this. Okay, so you add some noise, you try to denoise, add some noise, try to denoise. Okay, and then you have variation autoencoders. So this is where it kind of began. Variation autoencoders came first, and we'll just get into some detail on it, and I'll just try to drive down the point of what is different from classification and generation. So autoencoders, autoencoders, basically what they do is you just go from input, you go to an embedding space, and then you decode, and then you have the output. And what your main objective is in the case of classification is to make sure that your input and output is same or similar, right? So this is a reconstruction loss, and it can either be cross entropy loss or mean squared, sorry. And what you want to do in autoencoders is you want this encoding to be able to identify this. So you want it to differentiate and identify, different numbers, for example. So this is from the MNIST number data set. So 0, 1, 2. So if, the numbers change, then the encoding has to change in such a way that it can help the decoder regenerate the input. So this is, again, classification. How do we go from classification to generation? So if you see this image, this is basically just showing you, what this encoding space is all about. So if you take that encoding and you kind of project it into a two-dimensional space, then you'll get a scatter plot of like this. And this is clearly giving you these boundaries, right? So you know that 1 is here, 7 is here. So again, this is not going to help you in generation, but this is surely going to help you in classification. So to go from classification to generation, what there was this variation that was introduced in autoencoders. Okay, so instead of just trying to get the perfect encoding, what we're trying to do is we're trying to learn the distribution of the input. So apart from 0, we also want to learn a slight variation like 1. We want to know what 1 looks like or what 8 looks like. So we want to kind of create different zeros, different ones, different 8s. And to do that, we're going to learn the distribution, the mu and the sigma of the distribution. And if you see here, uh, if you consider this is a sample output. So this sample means sample sigmas. And then what you do is you have these normal distributions with mean and variance. And then you just sample from this normal distribution. So what do I mean by sampling? So if you look at this, right? So this is, for example, this blue one is normal distribution, and sampling is just basically stopping somewhere, okay, any random point, and just selecting this value. So this is 0.7, for example. So that's what I mean by sampling. Okay, so basically there's a curve over here, and you're just selecting a random value from there, which is 0.28. Okay. So you create this sample, and then from the sample, so this sample, if you see, it will be slightly different from what this is. Okay, so you're going to create this sample, and then you're going to go do the reverse process and generate your output. So this diagram explains it even more clearly. So here, in the standard encoder, you're just trying to learn the point, whereas in the variational encoder, you're trying to learn the mean, right? The distance from origin, the magnitude of the vector, and then you're trying to learn the sigma, how much it varies from the mean. Okay, so apart from just learning about zero, we're also going to learn about slightly different variations of zero. So if we train variation autoencoders, this is what we want to get. We want to get distributions that are close to each other, so that the derivative that you take is continuous, and there's no discontinuity, etc. But there's a chance of this happening because the model will try to just discriminate. Okay, because you're trying to, if you just use the reconstruction loss, right? If you just use the reconstruction loss, then what's going to happen is you're going to end up here somewhere, because again the model is trying to form clusters, like how it's forming clusters here, just to discriminate. Okay, so what do we do to avoid that? So we add this other loss uh, function. This is the callback divergence, and what this basically does is it just measures how much two probability distributions diverge from each other. So in the case of variation autoencoders, what we do is whatever means and sigmas we get here, right? We try to keep them close to this blue one. So we try to keep them close to zero mean and unit variance. Okay, this is the derived formula of that. So we try to keep it close to here. So if you see this, this red line, what we penalize is we'll penalize this red line. The further it gets away from zero mean unit variance, we penalize it more. Okay, so then we try to bring it back closer and closer. That way, if you see, the distributions will be sort of around your origin, and they'll have similar variants basically. Okay, so if you just use KL divergence as a loss, then what's going to happen is your embedding distribution is going to look like this. So this is again not very useful, right? There's you don't know where to generate from. All the samples are very in the same place around zero, etc. So so if you add the two together, right, if you add reconstruction loss and KL divergence, then you're going to get a desired embedding distribution. So over here, if you see, there are some nice clusters formed. At the same time, they are close to each other. So for example, if you want something between 1 and 2, you just take a sample literally between 1 and 2. Okay, you take this, you find out what the mu and sigma is of that Gaussian, and then you just sample from there, and then you just put it into the decoder. Okay, sample from there, put it into the decoder, and then you'll get something like this, which is a image between 1 and 2. Okay, so this is how you generate with variational autoencoders. So I'll just pause here if anybody has any questions on the topics we covered till now. Okay, okay, thanks. So now we'll just get into a different methodology to generate data. So if you remember in this model, in this image, we had variational autoencoders. They're fast sampling and they're good at creating diverse samples, but they can't create high quality samples. Now we're kind of going to look at this generative adversarial networks, which is very different from this encoder decoder architecture. So if we come to GANs, what's happening is GANs basically consist of two models trying to play a game. In this, the generator model is trying to generate samples, and the discriminator model is trying to differentiate between generated samples and real samples. So, the generator will generate a sample, then we'll create a training set for the discriminator. and then the discriminator will either say yes or no, and it will then update the model. And depending on what the discriminator output is, we'll be updating the GAN model so that it can, create even better samples that are very close to the real sample, to real examples. So the problem in this is that the GAN, because of the adversarial nature of this paradigm, what happens is the GAN tries to learn one particular sample that's going to fool the discriminator. Okay, so it tries to learn the best sample that the discriminator will get fooled by. Because of that, what happens is, then if you go back to this diagram, we lose this mode coverage diversity because it's trying to create that one, golden sample uh, that's going to beat the discriminator. So there are some techniques that are used to, avoid this, to prevent this. But yeah, so you see, like, there are these three different sort of methods that we have covered. So one is diffusion denoising, where we're adding a bit of noise, denoising, adding noise, denoising. Then we have variational autoencoders, where we're learning this distribution, right? Which is, we're learning the mean and the variance. And then you have GANs. The GANs, what they're doing is they're just trying to basically, they're playing a game. So one is trying to create a real sample, and one is trying to make sure that it knows that this is a generated sample and not a real sample. So this is pretty much all about image generation. If there's any questions on this, because we'll be moving on to text generation next. Okay, cool. So what is text generation? So to understand text generation, we need to first, understand what language models are. So language models, what they do is, they're given a large corpus of text, and you just want to basically predict what the probability is of a word following, a bunch of words. So in this case, the car drove into the driveway. This seems like the path, highest probable path. But again, this depends completely on your training set. So the large corpus of data, whether it's Wikipedia or books, for example, if they have a lot of samples where the car drove into the driveway is there, then this will have a stronger, basically stronger line. So then the chances of this being the sentence is much higher than the chances of it being parking lot or garage, for example. Okay, so in language models, you basically give a large corpus of text, and you're just trying to learn these probabilities. That after parking, the chance of lot coming is 80%, whereas the chance of garage coming is 20%. Okay, so now from words, we need to go to some numbers, right? Because you can't do maths on words. So how do we go from words to numbers? The initial step in natural language processing is you take the words and then you tokenize it. So you basically break it up into tokens, and tokens are in your dictionary. So you have a large dictionary of tokens, and each token will represent a class. Okay, so now what you do is you take these tokens, and you're going to train an embedding model. An embedding model is basically taking the token index, the token class, and it's creating a vector. Okay, embedding vector. So this is the input that goes into your into your LLM in the case of neural networks. And this embedding model can be anything. So it can even be like one hot encoding, right? Where you're just saying that the first word, if you're if you embed object one, for example, this will be 1 0 0 0. Object two, this will be 0, this will be 1 0 0 0. So in when you do it like that, the problem is there's no semantic information, like there's no information about the relation between these two objects. So embedding models, there's various ways to train them. There's word to vec, then glove. So Now, these are all different methods of training them such that the embedding has some semantic information so that the LLM or the model that you're training is not starting from scratch. It's starting from some information at least. So now, embeddings basically go into the transformer. What is the transformer? So if you just see this Drake meme, we're not talking about the movie Transformer, but we're talking about this architecture. And this was invented by Google around 2017. And the main thing about this is the main building block in this is self-attention. Okay, so you see this multi-head attention block, right? So in this, the main building block is self-attention, and we'll just get into some detail. And the reason why we're getting into detail on about self-attention is because if you read any generative model paper right now, the first thing you'll see, or the thing that you'll always see, is an attention block. Okay, so every time you see an attention block, if you know how self-attention works, then you'll be comfortable and you'll be able to kind of understand the paper. Okay, so what exactly is self-attention? Now, if you look at this sentence, the animal didn't cross the street because it was too tired, right? So self-attention is basically associating words within the sentence with each other. So in this case, it has a strong has a strong association to the animal, right? Because in the latter half of the sentence, it was too tired. So you need to know what it is. You need to know that it is the animal. So in when you learn this self-attention block, what you're trying to learn is you're trying to learn this association. So you see, this is like colored orange, whereas for example, because, right, the relation of it to because is almost zero. Okay, but it to animal is very strong. So how do we do this? So first, we take the word, we go from word to embedding using any embedding model that makes sense to you. Then we take this embedding and we break it up into these three parts. So you have your queries, you have your keys, and you have your values. Okay. What the self attention block, where the learning happens, is in these matrices. Okay. You want to learn a weight, uh, a weight matrix for Q, a weight matrix for K, and a weight matrix for V. So how do you go from X1 to Q1? You basically take this and you matrix multiply into this. Okay, so this is a what? This is a 1 cross 4 vector, right? And this is a 4 cross 3. So if like uh, matrix multiplication, then the inner dimension cancels out, right? So 4 and 4 cancel out, and you get a 1 cross 3 vector. Okay, so why have they used these terms queries, keys, and values? This is because they want to try to kind of relate this to the database query realm. So in database also, what you do, you have a query, right? You want to find the key that very, like, you'll take the query, you'll try to match it with all the keys, right? You'll try to see which key is having a high relation to the query, or which key satisfies this query, and then you basically fetch the value, right? So similarly, you have queries and keys here. Queries and keys are basically used to kind of score the value. Okay, so if you see that, what happens is you take the query, you take the key, and you do a dot product. Okay, if you see it, this is a dot product. So you take Q1, you do dot product with K1. You take Q1, do dot product with K2. So K1, K2, you can imagine as indices or columns in your database. And what you're doing is you're taking your query one, you're multiplying it with all the columns or all the keys basically. Okay, and you're trying to find the key that has a very strong association to this K1. You're trying to find the key whose product will basically create a large value. Okay, and then so this part is like you're dividing by 8. So this is something that they found out to keep the numbers small, because the numbers get too big, then the maths will become unstable, for example. And then what you do is you take this and then again you squeeze it in even smaller, and you softmax operation is basically you're taking a vector, you're taking the numbers and you're just converting it into, you're squeezing it into zero, between 0 and 1, such that the sum, okay, such that the sum of those output scores is equal to 1. So you're basically making it into a probability distribution. Okay. So Q1 into K1, so high association with itself, right? This word has a high association with itself. And Q1 into K2, it has some association. But if you see this relative scoring, this is like 88% you can consider, and this is 12%. So what are we going to use this 88 and 12% for? We are going to use this to basically multiply into the values. Okay. So we want to multiply this 0.88 into V1. We're going to multiply 0.12 into V2. And then your final output is basically V1 plus V2 plus V3, like depending on the length of the sentence, so on and so forth. Okay, so if you see, right, V1 is, you can see the color, it's slightly, it's a strong shade of blue, whereas here you can see it's very faded, right? So this basically means that if you add V1 and V2, V2 is going to have a very like small influence on the final value of Z, right? Z is going to consist more of V1 than it's going to consist of V2. So again, if we go back to this picture, right? So what are we trying to learn again? So what we're trying to learn is if it, okay, just consider it is your x1. So if it is your, sorry, let's just say animal is x1, okay, and it is x2, right? So if it is x2, we basically want to learn a query matrix such that q2 into k1, okay, is a big value. So what we try to do is we try to learn W and WQ and WK in such a way that these two create Q2 and K1, such that the dot product of this is a large value, and that dot product large value will be multiplied into V1. So now this word, basically the animal, the animal, this word is going to have a strong association to the final output, that is Z2, right? So because it will be like highly colored, whereas the other words will have a small weightage. Okay, so we are just using Q1. We use the query and key as weights, and we multiply it into V1, and then we finally add them all together and create Z. Okay. Now from self attention, we go to multi-headed attention. So why is this needed? It's because like in this image will make it clear. So if you see this, right, it is related to the animal, but it is also tired, right? So you want to learn different rules of grammar using the different heads of attention. Okay, so like for example, this is like the noun, you are associating it with that, whereas here it's the animal is tired, so you want to learn that that rule of grammar, for example. So you have all these different heads of attention, and they're all like learning slightly different things, different rules of the language, of how the language works. Okay, so this is your simple self attention. Then you have multi-headed self attention, so you learn all these blocks, and then each of these blocks, all of this together makes one encoder, and then uh, encoders are stacked one upon one on top of each other. So we see here, right, encoders are basically stacked one on top of each other. There'll be one here, there'll be one more here, and then you have decoders. So the output of encoder 0 is basically R that goes into the input of encoder 1. Okay, and then so on and so forth. So finally, you're getting this Z matrix. And if you think, right, so you might think that, okay, if you have many multi heads of attention, then your model is going to get better. But there is a compromise, which is basically the speed and efficiency of the model versus how good the model is. Because as you see, right, this weight matrix, the final weight matrix that takes all the Zs and kind of compresses the data into one output Z vector, Z matrix. This weight matrix can get extremely large. So this is the limitation. Like for example, even if you use Chat GPT, right? You've basically pasted a large amount of text, and it says this input is too large. So this is what limits that input. Learning this big weight matrix, because not only does it depend on the length of the sentence, it also depends on the heads of attention. Okay, so because of this, you can't really have many heads. So there is a trade-off where you need to kind of hold back. Okay, so again, this image I think we discussed. Uh, so now we'll just talk about Falcon 40B. So Falcon 40B is an open source LLM that has been ranking #1. So it's beat OpenAI, Google, Palm, and all of these. And again, right. So the main thing in LLMs is basically understanding attention. So in Falcon 40B, we have something called multi-query attention. So what they have done is, instead of having these separate, uh, you know, weight matrices for Qs, Ks, and Vs, instead of having separate queries, keys, and values, what they have done is they're just having a shared key and value embedding. So this, reduces the size of the network a lot, because you're sharing the weights. Okay, you're sharing the you're not keeping different matrices basically for the different heads. So now that you're sharing the weights, the size of the model reduces. And this, if you see, this is just a decoder architecture. So after transformers came, and after people started experimenting with this encoder decoder architecture, people started basically finding out that decoders, just plain decoders, work better than this encoder decoder architecture. So even GPT OpenAI's model, for example, is just a decoder model, right? So even this one, Falcon 40B, is just decoder. So finally what you do is you calculate your attention, your scale dot product attention, and then you concatenate all of them. So that's what's happening here, right? You're doing this concatenation, this z0 z1, you're concatenating everything, and then you're putting it through a linear block. So that is this, right? And then finally you get your output. So then you can just basically put z through a softmax, and you can classify it. You can use it for language model. So that's like, in the case of language model, what are you learning? You're trying to basically learn, let's go back. So basically you're trying to learn this. So like I said, right, you're trying to learn this token class. So you'll be passing this as the input, and you're learning this predicted token. You're trying to predict that, right? So depending on your use case, uh, you can basically replace this part, right? You can remove this top and then just fine tune the model. So all of this will be the same. We don't want to really mess with these weights, because this has been trained on a lot of data, right? But you can change this depending on your application. And the one interesting thing about Falcon 40B, basically it was developed in collaboration Hugging Face in UAE. And one of the main things that they did is they have used very high quality training data to train this part. So they have not just blindly used large corpus of text or just a dump of the internet. They have done a lot of pre-processing to the training data, like denoising it, deduplicating it, and I think because of that they have a very strong model. So this is all about self attention, and self attention goes into the transformer model, and then the transform model is just basically different. You can just read about the transformer. GPT, for example, is like, again, pre-trained transformer. So once you understand this self-attention block and you understand multi-headed attention, then you can basically understand any of these transformer models, and you then pretty much know uh, text generation and LLMs. So I have all the references here. We'll send this to you as an email to all the people who have attended, because these were very good, and I have not created any of these images except for this image. Okay, but yeah, all these images and these references are very good. I would encourage you to go and read them. Okay, that's all I have. So any questions from anyone?
Can you please explain a bit about Falcon 40B?
Yeah, sure. So Falcon 40B, okay, let's go slightly more into the detail. So you know this query, this key, and this value concept, right? So now your query is basically, they have kept the query part separate. Okay, if you see, right, these different colors. So linear basically means this. Okay, wherever you see linear, right? Linear basically means this block. So when we do this x1 into wq and you get q1, that is this linear block that they're talking about. Okay, so they have maintained the different, so again, right, multi-headed self-attention or multi-headed attention. So they have maintained different blocks for the query part. So this part, for example, sorry, this wq, right? So w0q, w1q, w7q, so these are still different. All right, but what they have done is, if you see this, right, this linear operation and this linear operation, so these are the same color. So what they have done is, they have, instead of having different weights, like different matrices, like instead of having w0k, w1k, they just have one w0k. Okay, so that's a shared weight. So what will happen is, you're just trying to learn just one of these for k, and you're just trying to learn one of this for value. So shared weight is a concept in in deep learning. It was actually, it was initially used in convolution neural networks also, where you have like shared weights. The kernels are shared. Okay. So similarly here, what you're doing is, you just have one of these, you just have one of these. Okay. So now you can see, right? This is going to drastically reduce the size of this. Okay. Finally, what you do is, you do the same. You do like pretty much the same thing. You do q1 into k1. Okay. You get some score, you score the values, and then you add the values and you get your z. All right, so that is your scale dot product attention, right? Same thing. What are we doing here? We're doing dot product, and we are scaling. We are basically multiplying this output into the value vectors, right? And then we are adding it. Pretty much same thing happening here. Then concatenate. Again, what you're doing here is just concatenating all the outputs. Then finally, you're doing another linear operation, right? Which is this. Doing another linear operation, you have your output finally. Then this again, you can put into you can again put this into a linear thing, linear operation, like over here. And on top, you can put a softmax layer. So this softmax layer will basically predict something. So whether you want to predict the class of the sentence, or whether you want to predict the next token. So in the case of chat, what you do is, you will take, how does chat work, right? So you'll take multi-query attention, right? That's your input. Then you'll predict shared. Then next, your input will be multi-query attention shared. Then you'll predict key. So you can keep basically increasing your input and getting your chat completion. Okay, so that's Falcon 40B. One of the things about it is this shared weights, this multi-query attention, and they also have something called flash attention, which is again a memory optimization. So you can read a little bit more in detail about what flash attention is. So does that kind of answer your question?
Yeah.
Okay. Any other questions? The vision transformer. Yeah, so in vision transformer, I mean, the concept is pretty much the same, right? Instead of having these embeddings, you will basically have a convolution neural network. Okay, so what is your convolution neural network going to do? So if you go here, so you'll have a convolution neural network. You're kind of going to come down to this. Okay, you're going to have many of these because each kernel is going to give you a channel. So you're going to have many of these small matrices. Okay, all different channels learning different shapes. So in the case of language, what are we trying to learn? We're trying to learn different rules of grammar, right? We're trying to learn different rules of grammar. In the case of images, we are trying to learn different shapes. For example, you want to learn that, this is circle. So depending on the level of the convolution block, you'll be learning slightly more complicated features. Okay, so that's what your kernels will be learning, right? Then finally, you will have many of these small matrices. And what you do is you're going to flatten them. You're going to take these matrices, flatten them, and create one embedding. Okay, so that is now your embedding space for your vision transformer. And then what you'll be doing is you'll be doing similar, you'll have similar attention blocks, and you'll have all of this add normalization, position embedding. So you'll have similar things, which will basically be used to, finally create your output, which is your Z. So that can be either in this form, and then you'll have, again, on top, you'll have a soft max or something. So it's just kind of the way you go from words to embeddings. You have to go from image to some sort of embedding again. And in that case, you'll be using, again, coordinates, because that has worked very well. And in the case of images, right, the attention is not depending on what problem you're trying to solve. So in suppose you're trying to solve a problem where you have videos, right? So transformers are good at sequence learning. So a video is basically a sequence of images. So that time you want attention to be learned across the sequence of image. But I think what you're trying to ask in vision transformers, the attention is learned in within the image itself, right? So for example, if you go to let's go to Drake's image, right? So here, what you're learning the attention, like, this is a face and this is a hand, for example. So you're trying to learn, these associations. So for example, in a pose estimation transformer model, you want to know these associations because you want to kind of estimate the pose, right? You want to draw this stick figure that says, okay, this is his hand and it's coming out like this. Whereas in this case, his hand is coming like this. So you want to learn these associations. So your self attention will be within the image. So again, it depends on whether you're learning uh, across video samples, like you're learning across series of images, or whether you're learning within. Do you, is that does that answer your question, or do you want more detail? Okay. Any other questions? Hello. We're good. No more questions, right? Okay. Cool. Thank you. So now I'll hand over to Vishal.
resources, which is the standard for healthcare data, which is recommended by WHO. We are working on that, and in those we use those libraries from Google, which I mentioned just now, that Fire SDK and Fire Analytics we mainly use, and we are also the core contributors in that library. And yeah, so why prompt engineering? So basically, prompt engineering means how we structure our question or the statement that we give to the LLM so that it can understand better. So it is not more about the engineering stuff. It is just like paraphrasing the English word in a such a way that the model can understand better. So yeah, and why it is important, because the way I give the prompt, my response will be dependent on that. So I and of course, so one is content personalization. So if I want to get some personalized content from the LLM, it all depends on my prompt, and also the cross-domain versatility. So this is one advantage that we are getting from Gen AI and LLM is that no need to build the model again and again. Just by structuring your prompt, you can get various information about the various domain in the single model. And yeah, these are the some just funny use cases that we tried to figure out how prompt can be designed efficient. Like just I have asked the ChatGPT to give me what is 124 into 675 into 985, and it gave the answer. Like if we directly just look at it, it gives in such a way that it looks very realistic. But that is the wrong answer, as we have feature from calculator as well. But in the next prompt again, I made it like, if give the answer you are only 100% sure, otherwise just say I am not a calculator, then it said I am not a calculator. Like, yeah, this is just one some funny use case that we tried. And then you can see, I don't know if it is visible clearly in the background. Here I just said like some about the place, that place is not good something, and so it said it gives some large story which is nowhere related. But the same prompt means, by using efficient prompt we can make it like a classification model we can use. So in this I just mentioned that if the place is good, then that is a positive feedback. If the place is bad, then it is negative. Then if it is upright, then neutral. And then I gave the same statement and just colon and empty. Now it is classifying it as a negative. So this is just one example how we can use these prompts to make a classification. And yeah, there are also some use cases like just I copied some review from the book my show, like which has a 3 rating review, and just I pasted all the review here and I asked what is the rating for this movie, and yeah, it is also 3 rating and gave it as a 3. But also some use case I have just taken one review from 1 star, but that also it classified as 3. And in this case, there can be a human error as well. Like I'm copying the review from one rating, but if that person is written good review, then it is going to classify as good only. So this can be a human error as well. So just by experimenting all this stuff with the prompt and all, then we thought of using LLM for a healthcare benefits. And as I said previously, we work on OHS, that is basically for to develop the healthcare in Nigeria. So currently in Nigeria, health means people not visit the clinics very frequently. They go for some traditional practitioners and all, and also they do a lot of paperwork, and it is like very difficult for healthcare worker to maintain all those records. And also we thought of coming up with the application design, and Yeah, and we have just developed one Android application in association with Google that is Impact Health. So this is provides the basically management of pregnant women's healthcare in Nigeria. In this, we all use the data standard which is FHIR. So that is recommended by WHO again. In this, I'll just show how we use these prompts and all. Okay, so as I mentioned, people not frequently visit the clinics, and there will be some healthcare workers who go out for a campaigns and all. They visit to the patient and they collect the information, and if there are any risks or something that need to be concerned, then those healthcare workers gets connected with nurse or doctors. But the case when doctors are not available or nurses are not available, healthcare workers can make use of the AI. So this is being designed like kind of a chatbot, and so just we say in the initial prompt, and I can't show here because it is a video demo, but whenever we pass this initial prompt, in the background along with the prompt we are also attaching all the patient's information whatever collected, for example BP, temperature or pulse oximeter kind of. So then when I say patient has fever, it will give some response. Yeah, it will say something like if the fever is there, and since I am using the patient is currently pregnant. So for pregnant women in Nigeria, it is common that they might face malaria, and so it gives the advice like try to perform check the malaria if it is positive or something, and then to give the paracetamol tablet. Uh, this is the response we get, and again if we say, so then we are just saying malaria it is negative, and then I had given the paracetamol tablet to the patient. Okay, then so after the conversation, again if we want to summarize, then we are just asking for the ChatGPT only to summarize this whole conversation, so it will summarize and we are saving it for the future reference. Yeah, so this is one of the use case, and another use case that we are currently experimenting means it is not complete. So one more use case we are experimenting is we have just the reason behind this experiment is as I mentioned, in Nigeria, country like Nigeria, people don't usually go to the clinics. They go to some traditional practitioners, even in a pregnant woman. So all the idea behind this is somehow to get those patients to the clinics. And as we know, it is like in nowadays it is a common case like we can send a message, WhatsApp message or SMS to keep in touch with the patients. But if we are sending the same format again and again in the same message, they just sometimes they look and they start to ignore the messages. And also it is not possible for some doctors or any healthcare workers to go over all the patient records and create the personalized messages. But here we can use the LLM to create the personalized message based on those patient conditions. So for this experiment, we have used some three use cases. One is patient who is pregnant and has long gap between her two AMC visits. And so one more use case we tried is the patient with hypertension who has high BP. And another use case is the patient who is suffering from hyperlipidemia and anemia. So when we just go over a patient, so here you can see all the patient records that are collected till now, and based on this patient's record we are just generating the prompt, and we get the information, some personalized information that will makes feel patient, like if it is a very personalized, then patient may feel like visiting the clinics again. And in this, again, if we want to see just how the prompts means how the LLM interact for different use cases and all, we can just edit some information. So we can just regenerate that now. So based on the information we changed, the prompts will get updated, and just we want to see the previous one, we can go to previous. So we can see like how with different information we get the different answers. We are just experimenting with this. We tried with the text DaVinci model, also the GPT 3.5. So we need to try with 4 as well, means how which one is more better and to find out. So this is one of the use case we tried. Like, you have any questions related to this? Yeah.
First of all, great presentation. I have very in the start, when you said you started collaboration with Google for 9 years. So at that time, anyone before developing your app or anything, you would be user research there.
Sorry.
User research.
Yeah.
Done the user research.
Yeah, we have done the research and we found.
No, not research. User research, it comes under the umbrella of UX.
For your question, the Kashyap will be better to answer. Yeah.
What's the question? So before developing the app, right, you said that you started collaborating with Google for developing health app for the Nigeria, right? So for before developing, the first step is what are the requirements, right? That you go, because this is a very, I would say, abstract. This is a general problem in India as well, right? In rural, we do the same, right? So the question was
are there any efforts on that?
not efforts. Before developing, what are the user research that has been made? Before developing.
What are the maths?
Yeah, exactly.
Whether there are takers.
Yeah. So yeah, one
What was
use case
their
was
previous process? Okay, now even do they need app? Right? That is the question. Right?
Okay. So yeah, for that question, the one use case, their technology is still far behind, and not everyone has the computers available. And second thing is the internet state is not stable in Nigeria.
Okay, so
Yeah. Yeah, Kashyap. Kashyap, you can go over.
yeah, I can take this question. So I'll just repeat. Yeah, can you hear me?
Yeah.
Hello?
Yes, yes,
Yeah, sorry. So just to repeat the question for the online audience, I think is whether we conducted any user research, right, before.
Developing.
Kashyap, you are not audible. Yeah.
no, he's not audible. Is your mute?
Yeah, sorry. So basically, the user research that we conducted, we didn't do it in collaboration with Google. So we have been in Nigeria for the last 2.5, 3 years. Uh, is there echo? Is it my echo? I'm not sure.
You're audible.
So we have been there for the last 2.5, 3 years. So there was a team from Google, UX team. We work very closely with them, and we went there. We did some interviews of the healthcare workers who work there. We also did interviews of the community workers who work there, and we also took interviews of the Ministry of Health people. So the Impact Health project is basically not just for healthcare workers, it's to reduce the time taken for important health indicators to reach the Ministry of Health. So our main clients over here are the Ministry of Health, right? So they want to really, get the indicators really fast, and they want to digitize the primary healthcare that is there in Nigeria right now, which is basically based on big registers and big books. Okay, so we did all this user research, and in apart from Google and their team doing the research, we also did the research. And one interesting point is that there is this in Nigeria, right? There are many foundations, many programs that take place at primary health centers, and usually the nurse is overburdened, with all the work. So she might have many physical registers to fill up. She might have 2 or 3 apps to use. So we have tried to, make our app as basically the user interface as intuitive as possible. And that has basically gone into open health stack. So there's a library there's a library that's part of the open health stack, which is used for data capture, which is seen by those healthcare workers. So that was the user research that we conducted, and we also spoke to them to get to understand in more detail. Even all the workflows that we create, we always basically talk to them first, and we ask them whether it makes sense. So another example here is outpatient. So in outpatient scenario, ideally what you would imagine is that the patient is coming in, and then you have a case file that is open for the patient, and as you do things to the patient, tests, etc., you keep putting information into that case file. In the case of Nigeria, when we asked the healthcare workers, they said that this system is too complicated, because for them they are used to just filling in data as and when the patient is going out. So while the patient is going through the health receiving process, they will be filling in a piece of paper. Then finally, when the patient is heading out, they'll just take all of that and put into a register. So we designed the workflow uh, in such a way that it's not complicated. And what they said is that later on, as people get more comfortable using apps and digital systems, we can slightly improve the workflow. So I don't know if this answers your question. Uh, so,
So, yeah, understood. Second, along the second question with that is, uh, currently, like the demo that is shown is on English, right? So how good the workers, like the health workers with the English? That is the question, right? Because like even giving the input, like whatever you have, right, is based on the one thing is that is like giving that input, right? So health workers should be consider that as well, right? Because this is like we know, like in like at least in a good manner, like okay, this is what we are doing, and then we get something, right?
Yes, like this is the experiment that we are doing, and it is not.
Yeah, can you just repeat the question? Actually, can somebody give him the mic? Couldn't hear properly.
So the question is like this all application we are developing in English. So how good it is like healthcare workers all understand English in Nigeria?
Yeah, so in the case of Nigeria, English is the main language that they speak. They have their regional languages that they speak, but officially all the documents, if you see that, those are in English. So the healthcare workers and the people we hire basically for this kind of work, the basic requirement is to read, write, and understand English. But to answer your question, what will we do if we were in a different uh, in a different locality? Then what we would do is we would use some sort of translator. We would also have we would use a translator only for the chat GPT part of things, but the input and the user interface and all of that would still be in the local language. We have done some experiments in to develop this app to support different languages. So we have also tried things with Indonesian language, and the library that we are using also supports different languages. So the solution what we have thought of is basically handling all the user input, everything in the local language, and the interface with chat gpt will have a translator in between which will translate to uh, English and then get it back, and uh, then retranslate it back to Indonesian.
Thank you, thank you.
Yeah, thanks for the question.
One last question. This is around like very basic. Like, should we? This is an LLM, right? So should we use LLM models for healthcare, or we dedicate small models? And did you did any comparison between like both of them? Right?
Sure. So in this case, uh, in the case of generation, I think LLM makes sense. But suppose we were doing some sort of action classification, then I think LLMs don't really make sense in that case, like because you can train a simple classifier. And I think the other point that I want to make is we did not use different uh, smaller models right now for this. We did not use smaller models right now. Sorry on this. We have not used smaller models or experimented with any smaller models. But this demo was mainly to show the strength of ChatGPT. Uh, but like I said, so in the case of generation, I would still stick to using LLMs. But again, depending on the deployment scenario, whether like for example in Nigeria, internet is not great. So to be honest, without having a strong internet connection right now, at least it's not possible to run an LLM. And even the phones don't have strong high powered GPUs. So this solution is limited.
Thank you, Vishal. Thank you.
Okay, I have one question right now. The demo that you have just given regarding the app. So the patient are asking the questions, correct?
Sorry, it's not the patient; it's a healthcare worker.
Okay. So if the healthcare worker just type any question, how we are analyzing that it's a prompt? Means you are just getting the data from ChatGPT or ChatGPT APIs or Google OpenAI?
No, it ChatGPT.
ChatGPT.
Yes.
So how we analyze that it's a prompt question? Means it can also answer some other kind of
No, but in the application we have designed in such a way that whenever we are sending up questions, then that will be different, and when we get the response, that is different, right? we can make differentiate in the application.
And for that differentiation, have you used?
No, it is like just prompt will be the input that we send to the API, and whatever the response, that is the response comes from those APIs, right?
Okay. So the health workers can ask anything.
Yes.
It can be a prompt and it can also be
Yeah.
any of the free text.
Yeah, yeah. Those analysis and all means those filtration all we have to
So
do.
you are doing the filtration, like whatever they ask, the health worker asks, you are just asking, sending it to the chat GPT as a prompt, and
Yeah.
it will answer accordingly.
Yes.
Okay. And what is the why is OHS required over here? You are saying that you have also implemented OHS there, that is backed up by Google.
Yes.
Yeah. So what is the role of
No, that is not the role in case of LLM, but that is the all means to implement this application, and for that we started with the OHS, and then we are implementing LLM on top of it now.
So I can add to that answer. Uh, so one is we're not dependent on OpenAI in particular. So we can interface with any large language model. The second thing is yes, right now that interface, the healthcare worker can basically send any question, but we know that we have to build guardrails, we have to build filters to make sure that it is all specific to the domain of the questions being answered. And then regarding OHS, so OHS is basically the framework that is used to build this application. So one of the things in that is data collection, for example. There are different forms. So in healthcare, you have various types of forms. And if you want to have an application that has forms that are inbuilt into the app, then it's going to be very difficult because, for different use cases, you will have to change small things in the form, etc. So what OHS does is it helps you create these screens using a JSON. So then all you need to do is sync this JSON from the server, and you'll have an updated, data collection screen. And the other thing that it helps with is in the case of Nigeria, you have like offline, online scenarios. So, this app is built offline first, and every time it comes online, it syncs to the cloud, and all the data is sent to the cloud. And the third thing is OHS has been built in collaboration with WHO. So WHO has this concept of healthcare guidelines. So if you see, WHO publishes, these large PDFs, these large bodies of text, which basically tell, which basically help healthcare workers provide, good care. So in the case of pregnancy, antenatal care is, a very complicated, is a very complicated thing, and also it's long period of time, right? 9 months. So there's a lot of things you need to look after, a lot of things you need to take care of. And in the case of like LMICs, so lower middle income countries, everybody may not have that knowledge. So WHO publishes these documents, they are shared with the WHO team in the country, then WHO in-country teams, talk to the Ministry of Health, then the Ministry of Health will create some content, modify the content depending on the geographical location, and then pass it down to, all the health centers. So this long process is, trying to be cut short by using digital tools. And what WHO is doing is they are creating these smart guidelines, which are basically libraries. So you download this library, and it's a library for providing, positive pregnancy experience. So depending on the conditions of the pregnant woman, it will try to suggest the care plan. So in the case of, again, poorer countries where the healthcare workers, at the ground level do not have much knowledge, they'll be getting some advice as to what they should do to provide care. So this is, whole. This is what OHS is pretty much about. So Google and WHO collaboration with them, and we've helped develop, a lot of parts of OHS, and we're also working with WHO to basically publish and use these smart guidelines in Nigeria.
Okay, one last question on the ChatGPT. ChatGPT Okay, are you using any of the security in the middle of the chat GPT and whatever the questions are being asked? Because as we know, chat GPT is not safe. We cannot save anything to the ChatGPT because ChatGPT also itself training itself only, like from our data. So we are just saving the data of the patient, or we are just filtering the secret values of the patient and just asking some basic or common prompt to the ChatGPT for a client.
Yeah, great question. So this is just a demo. We don't have any of that, but an ideal solution would firstly anonymize the data, right? We don't want to send any patient information. Plus, I'm sure we won't be using like OpenAI's hosted GPT. So since there's open source models like for example Falcon 40B, right? So you can use Falcon 40B, fine tune. There's also Chat Falcon, so that is again open source. So you can take that, deploy it on your own server. Make sure all the data that is being sent is within your network and within your security. And to answer your second question, yes, guardrails and filters are extremely important. So, we cannot allow the HCWs to chat and just say anything, right? And also, we all know that, right now language models have this hallucination problem. So they can go completely off grid and sorry, off the tracks, and they can just start giving very random answers like how we showed, right, with the math uh, product value answer. So to prevent that, we will have to add filters not only while giving input to the LLM but also filtering the output, whatever comes out from the LLM. And I think another strategy to take in this is that we do want to get diagnostic information or diagnostic reports or any healthcare advice using these LLMs, unless it's heavily tested and maybe it's approved by some government body. So we don't want to use this to give advice. So you saw the nudge generation, right? The nudge generation and summarization. So we want to kind of target these low risk use cases so that even if there is some small minor mistake, then it's not going to really affect health, the person's health in such a extreme way.
Okay, one last question on the open source. That as we know that Falcon 40B or maybe Llama models, they will be very expensive because if we will host the open source models in the, for example, in AWS server, the server will eat all our money, is it? Because it requires heavy server usage and it will be more cost. It will be taking more cost as comparison to if we use any other APIs and all. So what would you suggest if we want to train our models as per it can answer as per our data rather than using the expensive open source models?
Okay, okay. So what I would say is that there is two things here, right? One is training the LLM, which is very expensive, right? That has lot of you need lot of data to train. I'm talking about the foundational model. So if you remember in my diagram, we had foundational models and we had what do you call it, specialized models. So training the foundational model is extremely expensive. That we don't want to do because the open source people have already done it. So you take the weights, you can even use the like you can even use the specialized model. Okay, you take the weights and you do inference. So prediction and inference is not expensive. For example, in Amazon you have Amazon Inferentia. So that is like basically it's on demand. It's not like a server with a big GPU that's running continuously. Okay, so you just use it, you deploy your model, and then you pay as per your use. So there's many, option. There are many service providers for this, where you just basically deploy your model and you use it only for inference. Even if you want to do it on your own server, it again is not extremely expensive. Okay, maybe it might be a one-time investment of getting a GPU big enough to just load that model. But doing inference is not an expensive thing. Training, of course, is a very expensive thing. Okay, thank you.
Okay, so just thank you all for attending. Can we have just some quiz session just to interact? So the just question is, which of the following model are foundational models? So GPT, ChatGPT, diffusion noise adding and denoising diffusion probabilistic model.
You guys have to answer.
Any guesses? Okay, let's see. The answer is A. GPT is the foundational model. And ImageNet is a generative adversarial network. Okay, convolutional network. Any other answers? We'll see the answer. And the third question is, variational autoencoders are good at generating fast and diverse samples, fast and high quality samples, high quality and diverse samples, slow and low quality samples. Okay. Any other guess? The correct answer is a fast and diverse samples. So, which of the statement is true in self-attention? Input words are on hot encoded vectors. Input embeddings are transformed into queries, keys, and vectors. Input embeddings are transformed into queries, keys, and values. And self-attention is only used in natural language processing. The right answer is C. And the last question, which of the above questions were generated by ChatGPT? Any guess? Any other guess? So, no, we have not trained anyone from ChatGPT. Yeah. So, this is all we had. Thank you for attending. I'll hand over to Mansi.
Thanks, Vishal, and thanks, Kashyap, for the session. I hope that was insightful. This is the last. This is the feedback QR code you can scan to provide us the feedback. I'll just like to add 2 lines about this QR code. So we generated this QR code using stable diffusion model. So this stable diffusion model, other diffusion model, they take actually text input and generate an image. And internally they do process of forward diffusion and reverse diffusion. You can read about it more. There are many open source diffusion models from like OpenAI have DALI and Google have ImageGen, so you can go through it. Apart from this, we have in the kit we have provided, we have given a feedback form. It will be very helpful if you fill and submit the forms. And apart from that, next we will be moving for a group photo session, and then we'll proceed for the snacks. Also, one thing, we are just flexing. In the kit, the pen which we have provided, that's a stylus pen, so you can use it as a stylus as well. Okay.
Also, we have a game-based demo here, so you will see Jackie Chan local, so you can have fun with it. It's right here on the screen.